To start, I would love to invite each of the panelists to introduce themselves, talk a little bit about how you define continual learning and self-improving agents, and feel free to connect that to what you're working on today. So we'll start with closest to me, Han Chen, and then we can move down the line. Thank you, guys.
Okay, so hey everyone, I'm Han Chen. I'm a first year PhD at UC Berkeley. I think continual learning is a very poorly defined term. I don't think it's a good term to use actually in your life. I think it's used so widely because it's very easy to raise money if you're a startup. If you just say like I'm a continual learning startup, it's very easy to raise money. That's why people I think people have been abusing the term for a long time. So I wrote a blog a few weeks ago on like defining this. I think there are actually like different type of continual learning, and the way to distinguish between them is actually how much you know about your future task while you're executing your current one. So I'll put it into 3 examples. So the first example is you're trying to solve a really hard science problem, which is like you're trying to say, let me solve like how do I create a protein that satisfies this property, right? You completely know the future problem, and all you're trying to do is trying to solve this specific problem, and you actually like you can try a lot of different methods. You can just keep retrying, best of n, or whatever you want to do it. There's evolutionary algorithms. Okay, so the second thing is like you know the future type of task, but you don't know exactly what the task is. So it's kind of like you have like a QA bot. You know it's like gonna be doing QA forever, but like you don't know what the question exactly is. And the third one is probably like, let's say you're a cursor, you have all these coding traces, and someone is sending you a new coding request someday. And then the problem is like you know it's coding, you don't know which repo it is at, and you're trying to improve the general capabilities. So I think like we actually want to separate these cases, because if we combine these 3, like I can have a benchmark that have like all 3 of them in there, but it doesn't show anything because it's like I'm comparing like whether this one is like a good English speaker with a good Chinese speaker. Like if I'm mixing them together, it doesn't make sense. So, but.
Yeah, thank you so much for the passing. I'm Roger, and I'm from UC Santa Cruz. I'm just graduated, and I'm previously doing the language model pre-training, architectural research. So I really agree that with him saying about the continual learning, that's the 3 different tasks. Because in the very beginning of continual learning, you will see that the continual learning has like the 2 different type of tasks. Like the first is classify image and like the cipherton or like the ImageNet. This is very very fundamental, like the beginning of continual learning. And now because the language models, like the emergence of language models is actually training on thousands of the different tasks in the whole like the whole website, in the whole like the whole web. So whole internet. So the continual learning becomes a problem that how you can continuously feed in the information into a language model and make it more adaptive to your field. I think this problem is still now not well defined because of KV catch is limited here, and your basically there's 2 ways to learning in language models. One way is using the gradients to learn. I think this is next one predictions. And second is using KV catch to learn. We are trying to minimize the gradient between key and values. This is like the mathematical formula of it, but there's 2 different ways. But mostly, if you like problem with the language models, you are trying to use the KV catch. But this cannot be continuously forever. Like for our human beings, like we can continue learning forever. But like for the tens of years. But for language models, they have the context windows. So I think this problems maybe is like the key problems continue learning now, and for language model part, because my field is mostly coming from that.
Hello, everyone. My name is Teddy Wu. I'm the co-founder and CEO of Intime AI. So at the Intime AI, we are the all-in-one genuinely AI platform to specific design for plenty of law firms. So we automate the whole the case life cycle. For example, right, analyze the record and draft the legal document, and automate the discovery process, and then to delivering the citation back. Legal research result all in minutes or hours instead of days and weeks. Right. In our context, the continual learning essentially is to continue improving the AI agent in our platform. So every day, right? Every day we receive a lot of feedback from our client. Right. So this feedback essentially is we'll consider as a very important benchmark for us to continue improving our backend AI agent. so that it's become better and better and deal with the thing that is more complex. So I agree that all this terminology essentially is very poorly defined, given the context. I just want to provide some information or perspective from the AI agent that are able to serving a real client.
Hello everyone, my name is Chong Kai Gao. I'm currently a visiting scholar at Stanford University. I'm a PhD student from National University of Singapore. My research is about robotics manipulation and continual learning. So for robotics, I think the concept of continual learning mainly care about two things. One is forward transfer, one is backward transfer. Forward transfer means if you have learned or trained on a lot of skills, can you learn a new manipulation skill faster than a model trained from scratch? And backward forgetting means if you are trained on a new skill, can you still retain the previous learned skills and do not forget them? I think this is very important for future robots. If you buy a robot in your home, you definitely want it to do some new tasks in your home. So it is very important to have a continual learning ability for that robot to maintain the pre-trained knowledges and also can perform new tasks in your home. So I think the current situation for continual learning in robotics is that we do not have such a powerful vision language action model than the LM in language area. So we know LM are usually trained for only one epoch or two epochs, but for robotics we'll still train it for maybe more than 20 epochs. So it is still overfitting the data.
Hello everyone, I'm Peng Tao Xie, co-founder of AI Build AI Inc. and also associate professor at UC San Diego. At AI Build AI, we develop self-evolving agents that can automatically build AI models. So given a task description, say I want to build an AI model that can predict the functions of proteins, this agent can automatically design a new model architecture, write code to implement this model, train the model, tune the hyperparameters, and iteratively revise the model architecture to improve the performance. Our agent achieved number 1 on the OpenAI MLE bench. It is a benchmark developed by OpenAI containing 75 AI model building tasks collected from Kaggle. So this agent is a self-evolving agent with the capabilities of recursive self-improvement. So every time it finishes an AI model building experiment, it analyzes the results, identifies the gaps in the process, and proposes a revised model architecture. Then it rewrite code to implement this revised model, and retrain the model, and reanalyze the results, and propose a further architecture. And this process iterates to continuously improve model performance. Because of this recursive self-improvement capability, the models developed by our agent is able to match the models manually built by human AI experts. For example, in Kaggle competitions for heart disease prediction or identifying salt deposit underneath the Earth's surface, the models developed by our agent are able to rank in top 5 or top 6 among 3,000 or 4,000 teams composed of human AI experts. I'm happy to share more about how we do continual learning and self-evolving in the following questions. Thank you.
Thank you all for the introductions. I will start with you again, Dr. Shi. So if you don't mind, I know you talked a little bit now just about how your work focused on agents that can design, code, train, tune, and improve AI models. In that setting, what is the difference between true continual learning and simply having longer context windows or memory buffers? Can you help us understand the distinction?
That's a great question. So in this AI Build AI agent, in addition to the memory module, which certainly is very important, we also have several equally important, if not more important modules that facilitate continual learning and self-evolving. The first thing is the continuous fine-tuning of the reasoning LLMs. Inside our agent, we have multiple small-sized reasoning LLMs that performs test time scaling and process reward modeling. These LLMs are based on the DreamPRM and DreamORM techniques that developed in my group at UCSD in the past few years. And with new data coming in, we continuously update or fine-tune these LLMs. The second aspect is we have a knowledge agent running in the background. It continuously go to the website, go to the web, read the latest papers, GitHub repos, and Hugging Face models to learn the state-of-the-art model design ideas. Then it dynamically and automatically creates skills for these new ideas and also continuously adapt them in the process. The third thing is the agent runs many experiments. Some of them are successful, some are not successful. And the agent is able to identify the model building strategies out of these experiments that can lead to better outcomes in the future. And the fourth thing is this self-evolving agent is a multi-agent framework consisting of multiple sub-agents that communicate and coordinate with each other. The pattern for these sub-agents to coordinate is also evolving dynamically based on the outcomes of the experiments. Yeah, so to summarize, basically our agent performs continual learning in terms of updating the weight parameters of the reasoning LLMs, generating new skills for the newly learned knowledge, learning from the past experience and experiments, and also evolving the coordination pattern of the sub-agents. Yeah, thanks.
Thank you, Dr. Shi. Very interesting work. Okay, Han-Chen, I'm going to ask you a question next. You expressed a little skepticism in your intro on continual learning, fairly so. And your work on self-improving agents and context engineering suggests that agents can improve without necessarily changing the model weights. When should knowledge live in memory systems versus skill libraries versus model weights versus somewhere else? Give us your thoughts on that.
Oh, okay. So I actually had this discussion back at iClear, so in April. So it was a similar panel. People were just like because like it was a workshop, and another paper was basically on self-distillation, which basically you need to change the weights. So the way the understanding that I am taking for myself right now is this. So a TLDR is that when the task is simple. So for example, if you're taking a task, for example, QA bar, on the same code base. So for example, like people are asking different questions about the same code base, then this is essentially something that is that is not that much information dense. So basically, the takeaways that you can get from previous runs is probably just like the scheduler code is somewhere in there, and there's a little bit of a trick that people did in previous runs. And if you write code in this way, it's going to break. So these things are highly expressible in text. So you probably can just do it in the text space. But if it's something that is more profound, for example, the fundamental coding capabilities, then you probably need some weight update. So this goes back to like why classification is important for these different types of tasks, because you would actually adopt different strategies. And a more mathematical understanding is this. So if we all, okay, let's think about like weight is essentially a bunch of numbers in a higher space. Each number is just like a dimension. And let's take the prompts as another dimension as well, right? So each prompt is essentially a token that constrains the generation. And the difference between a weight update and a prompt update is this. So for weight updates, you're essentially moving. Let's say it's a 1 trillion parameter model. You're moving in this 1 trillion dimension, and it's not constrained because essentially you can change whatever number that you are able to do. So if you move some number by a large margin, since it's like all mathematical like calculations, I don't know how familiar you guys are with linear algebra, but like if you move, let's say, some numbers by a large margin, perhaps the whole output will be greatly shifted, so it may just start spitting out garbage tokens. It's kind of like, you know, if I just change a layer in the middle by random number, it probably doesn't even speak like human language anymore. So you do not want to have like a very large update on the weight space, basically. So what you want is a very small incremental step. But the good point of this is that you can actually take this step by step. So if you are into economics, it's kind of like you can compound the effect step by step. But for the prompt update, it's actually a completely different story. So there are much less tokens. So the dimensionality is much lower. That like the freedom of change is much lower. And also, since a lot of the prompt updates, it's still generated by an LLM, which basically means it's human language. So you are essentially stuck in a very constrained subspace that everything is human language. And no matter what prompt you give to the LLM, like as long as you don't change the weight, it will always spit out text. So which basically means I can tell the LLM, you know, like you are a smart LLM that does this, does that, or I can tell it you are a stupid LLM does this or does that. I can do whatever I want in the prompt space, but the LLM will always be responding with text tokens. It will be speaking human language whatsoever. What it means is that it's actually in a very constrained subspace that you can do a lot of the wider jumps. So basically, I can like, if you think about it, different prompts are actually quite different from each other if you embed them in the space. So what it means is that it allows you to take bigger jumps, but these jumps may not necessarily compound with each other. So which basically means if you have a task that can benefit from, let's say, like a few updates, but you want these updates to be big, you might want to do it in prompt space. But if you want to do it in a really long horizon, let's say you want to take your experience from, let's say, 5 years, or like like right now it's like 5 months, it's not 5 years, 5 months of agentic rounds, you don't want to do it purely in the prompt space. You want to do something that actually accumulates these like small updates. Because if you do it in a big space, there are a lot of randomness, and in the end, like these randomness, you know, like if you do add them together, they kind of like compensate with each other, and you just end up getting back to the 0 point. But if you do it on like step by step on a smaller scale, it may actually accumulate. That's the whole point of a gradient descent, right? So you know, there are people saying that there's text gradient descent, which, you know, I don't really like think it's a gradient descent. But you know, hopefully that, you know, gives you like a little bit more understanding to what it's saying. But yeah.
Thank you. Appreciate that. And building on that conversation a little bit, Ruji, if you don't mind, I know you've done some work on something called looped language models, which I would expect that most of the audience does not understand. So if you could tell us a little bit about that, and how, if the weights are updated, or if we should think about this as a more powerful or efficient reasoning at inference time, just help us understand that a little bit.
Yeah, thank you so much. So what we are building for loop language model is something we trying to, if we see the transform, let's see more technical details. It's like if a transform is like a series of matrix and multiply each other together, and to just use once and generate one tokens. And we want to say, hey, if it's possible, we can stack two different like this transformers blocks together, like even they're identical with each other. So like the model will be recurrently reuse its self weights and like updates its KV cache. So in that case, the model is actually has like reused its own weights by 3 times or 4 times before the just 1 times for 1 tokens. So that's leveraged, making the models makes these models actually has more capabilities to in its own weights. So for example, we train our models like just like for 1 billion parameters, but we prove that if we just loop this 4 times, its performance, like especially on the the reasoning benchmarks, like what we are caring most about, like the Olympic benchmarks, like the Beyond Amy of these benchmarks, is much better than 1 billion models, and even equivalent to the 4 billion variants of models. And we train 2 billion models, and its performance is even better than 12 billion models. And this model is all industry level, like GIMA, Google GIMA, or like the Q1 series models. We find that even when we use small models, just reuse its own parameters, the models can become better and better. And I think one of the key reasons, for first reason, is that we call it latent reasoning, because in the whole reasoning process, you're using generating more tokens, and we want to compress the tokens into the intelligence. Like if you have 4 different tokens, you just explicitly roll them out, and they're just 4 tokens. But if we can just report 1 tokens, and this 4 tokens is all compute in the latent space, the model's capabilities is actually leveraged, like improve at 4 times, like as 4 times as large. This is the first reason, I feel like. And the second reason I think the performance is going better is, as this panel's topic, the continual learning. When you're trying to reuse the transformer blocks, is there anything changed? Actually changed. The different, even you reuse the same set of parameters, the KV cache of the language models is actually changed in the different times blocks. So you can equivalent make that, oh, the model's weight is actually changed with different type of loop. Like in the first loop, it's just the first KV cache. In the second loop, even the weight is same. The KV cache is changed because it's like even it's the same weight. So it's like somehow like you have the continual learning and improve its capabilities to learn the model performance. And for the future, which the loop language model can very good at, I feel like the model is very good at the first, we can actually is very good for more technical details. It's like we call the memory bounded devices. So like if you edge devices, your memory is actually limited to like the 1 gigabytes or 2 gigabytes. But if the model, they can only run like one B token, one B models or 1 billion parameters models. But for loop, you can make the loop itself. You can make this model as 4 billion as possible powerful because you loop itself. So this actually has been used, I think, in Snapdragon, and in like the some of them, like even like the I feel like I heard that Schema maybe is using the same tricks for some reasons. For Google Schema is trying to improve the edge devices capabilities. And second is that for if your models like for inference, we actually can have some tricks can make the loop 4 times models as fast as loop 1 more faster as loop 1 like the parameter models. So the inference time is even the same as the as like this just loop 1 models. So I think there's like the most important implementation is still like the edge devices, and because you're still limited to the memory, and also like for continual learning, for the power of comes from continual learning mostly, like because you have different loops, it's sharing a different KV cache, it's sharing different prompt space that, as like Haochun's mentioned, that they have its own representations on it. So this is like the loop language model. But so too long down the road is that we train models from just like 1 billion or like a model and its loop itself, and performance can, if they like loop 2 times, the performance is like as same as 2 times larger models. 4 times, sometimes it's not as good as 4 times larger models, and the parameter size is as the same as the models before. This is like how loop models works. Yeah, thank you.
Thank you so much. Okay, quick shift of gears. I'm going to ask Kongkai the next question. You've been mostly working on robotics, so we've been mostly talking about LLMs so far. But in robotics, the model interacts with the physical world. It fails, it retries, it has to transfer skills across objects, environments, and tasks. What does that mean for a model to genuinely learn from experience? And how do you really evaluate if a robot model has learned over time?
Thank you very much. So I think for robotics, the evaluation process is very different from LLM because robotics, they just do not have that large amount of training data. So for example, for the current state-of-the-art robotics model, they are only trained for their trained tasks. For example, maybe you have seen a lot of robots can fold clothes or fold shirts. But imagine a simple task that is unfold the clothes or unfold the shirt. I think none of the current model can do that because it is never trained. So this task may seem very simple to human, but it's totally a new task for a model. So for the evaluation of robotics manipulation research and the continual learning, I think the design of the evaluation should be should belong to several axes. For example, the variation of different objects, variation of different scenarios, variation of different tasks. And the real task is so complex that we cannot evaluate in a single benchmark, I think. I think we should evaluate in multiple different benchmarks, and finally we can get a good model.
Thank you. Okay, Teddy, last but not least, we'll shift to some more real-world questions and real-world production of agents and self-improving agents. You're building AI for legal and enterprise workflows. Mistakes, provenance, privacy, auditability, all concerns for you. In a real deployment, what does it mean for an AI system to learn from prior matters or cases or user behavior without creating unacceptable risk? How do you think about learning in that context?
Yeah, this is a great question. So the AI agent, right, when we try to apply to the real world, it really depends on domain, right? So for like the legal domain or medical domain we are serving, so there are some top requirements that each domain is very different. So in a legal domain, security, privacy, accuracy, latency are very important metrics for these domain people to consider, right? So for example, in the legal domain, the first thing you have to address really is about the privacy and security. So what we try to address this, right, essentially is to encrypt every data that our client upload to our platform so that no one able to see the data only client himself. So you create enough, 100% of the trust in client to use the AI agent for the task. So when you finish the first step, right, to build the trust, then you have to build an AI agent that able to automate the current workflow. They have to manually doing that every day. So one of the key things the client will care about a lot, especially legal professional, is accuracy. Right? You have to, the AI agent have to create a result that is almost like 99% of accuracy, but also with the variable citation link for them to take a look, so that they know that so the answer itself is correct. Right? So that is very, very important for legal domain. Why? Because if they submit some legal document to the court, and if they have false citation or resolution, they will get a sanction on top of that, even lose their job. Right? So that makes it a very serious thing for them. That being said, right? So yes, we have a lot of like AI native agent today are able to deliver some sort of result. So first thing we have to say, there's no AI agent today are able to produce 100% accuracy stuff. Right? It's always between like 60% to 99%. So the higher, the better for legal professionals really to adopt your solution. In other words, right, so in the backend, for example, so Intel AI today is a #1 choice for company litigation. Right? We're serving for the personal injury law firms, nursing home law firms, and many law firms. So one particular thing about this domain is they have very complicated long documents. That document have handwritten notes, they have tables, flow sheet, right? For any AI agent to read that, the first thing really is to using a very powerful agent to analyze everything first, and then to divide it into a small task, and then use a relatively cheaper or less powerful agent to continue everything, and then recompile everything into the final result. So in order to do a real, application-driven product, especially client-alike, so this is all the thing that the agent have to do. At the meantime, you have to evolving over the time, every day, based on client feedback.
Thank you, and thank you to all of the panelists. This wraps up our last panel of the morning, so please give them a round of applause.